All right. Okay. Start the recording. Hey, all right, folks. Thanks for your patience. Let's get started. How are we doing today? Good. That's slightly louder than the morning class. I can't imagine why. So yes. So a couple quick updates. So the Canvas page is still under construction. My plan is to get that all up today with all the information that you need. We're still covering the introductory materials. I do want to give you a few sort of course level remarks. So next class will be a remote coding session. Okay, we'll be coding in Python. I will be sending out a Zoom link that you'll all join. Okay, so that way you all can code from wherever you want. Heck, you can come to this class if you want and have a party. Okay, and well, you know, a fun coding party while you're watching me coding from my studio at home, or you could be in your in your dorm room or wherever kids live these days. Okay, and just participate live. We're going to be going through everything, coding top to bottom with no prior knowledge necessary. Now, for many of you have not coded in Python before, correct? That is okay. So what I'm going to do is I'm going to do a Python recitation, okay? I will be broadcasting it live, but it'll also be recorded so people can consume it at their own leisure, okay? It's be preferable if it's possible to watch it before Thursday. I know the timeline will be tight, but the earliest I can fit this in will be Wednesday night. So Wednesday night at 9 o'clock, you know, everyone loves partying or whatever they do at 9 o'clock, I don't know, or you can hang out with me, okay? And we're going to code up that gorillas game of monkeys throwing bananas at each other. Or I guess gorillas are technically apes. They're not monkeys. I don't know. Whatever. But we're going to code it up from start to finish, okay, as far as we can get. But the idea is to introduce you to how to use, particularly the Google Colab interface, how to use basic Python commands, how to do plotting, you know, assigning variables, the basics of what you'll need. And then we're going to on Thursday do some pretty basic Python coding for some of the concepts we're talking about today. Okay. Question. 9 o'clock Wednesday tomorrow. That is the definitive time.
Okay, and where are you streaming it on YouTube, or are you going to do it from
Zoom link for all of you so you can talk with me. Or on YouTube for your friends and family. Okay, all right. Great question. Skipper. Cricket, sorry. It's Cricket Skipper, not Skipper Cricket. Okay. Sorry, thank you. Other questions? Yes?
So for Python, are
Yes.
we able to like download Python itself, or is there like an extension that we would use, or like an online version?
Great, great. Let me clarify. So this Google Colab I'm talking about requires nothing other than a browser and an internet connection. If you already have Python installed you have Python interpreter installed in your computer, we have not covered how to do that, but some people know how to do it. You want to do that? That's great. I won't stop you. But I will say that there are sometimes technical issues with solving that we're not ready to solve with you, all 70 of you, just yet. Okay, so the easiest thing to do is just use Google Colab. We'll send out a link beforehand. All you need is a Google account, okay? And literally, you type code into the little script, you hit the go button, and it interprets it. Couldn't be easier. The only downside is there's sometimes just a little bit of like lag. It's not going to run as fast as your own computer. You can go back and forth, but it's just the easiest way to get started coding. My philosophy is that if you can get to hello world, you can do a lot. Okay, if you can't get to hello world, say print hello world, then you're in trouble, right? And this gets you to that really quickly. Other questions on Wednesday and Thursday? Okay, all right. Again, not required to attend. If you're already comfortable in Python, you know, maybe you have fun with me, and that's great. I love it, but you don't feel like you have to. But I know there are a lot of people who do not use Python, so I highly recommend it. If you can't attend Wednesday at 9, I totally understand. It's not part of your requirements for the course, but I recommend at some point consuming that as material for yourselves. And nothing is stopping you, by the way, from Googling some simple Python tutorials if you want to get started even before Wednesday. Again, you've all coded before. It's just a different language. Okay, question?
Sorry, what did you say about Wednesday again?
Wednesday, 9 p.m. is going to be a virtual recitation for how to code in Python. I'll be coding Python live. People will be theoretically there. Okay. All virtual. Yeah, tomorrow. Wednesday tomorrow. Wednesday tomorrow, 9 p.m. Me.
And how do you access it?
I will send out a link via Zoom. You may also watch via YouTube, but then you can only type in YouTube comments with the general public, which nothing wrong with that, but If I want to hear your voice, it's got to be on YouTube. Okay. And to be clear, YouTube will not be able to hear your voice. If you ask a question on YouTube, all that will be broadcast to YouTube is my voice. Okay. So for privacy reasons, don't worry about that. Okay. Unless you want to be famous. So, all right. Okay. How are we doing, Nick? Great. Cool. All right. So with that, let's get started on some basics of machine learning here. Okay. So we're going to try a couple of things today. Let's see if I can back this up here a little bit. So today, 2026, where does the time go, et cetera, right? So the basics, some machine learning basics. We did cover some basics last week, okay? And we're going to try something fancy today. I'm going to try to do some actual coding in front of you in a very sophisticated language, okay? So we'll see how this goes. It's a bit of an experiment, okay? All right. So machine learning basics, okay? Particularly, we want to cover the idea of capacity, training, and generalization. So, okay, so let's start with a hypothetical example. And a lot of us talking about machine learning in these examples, it's going to be pretty abstract. There'll be points on our plot. We love to talk about points on a plot as instructors because it's super, super basic. You can visually see it. But at the same time, I can also understand it's not very tactile. Points on a plot are not always, like, how does it solve the problem you want to solve with machine learning? How does it predict rainfall? How does it control my robot? How does it generate an image for me, et cetera? But we abstract it to these general plots. So the idea, so let's say you have some input x and some output y. Okay. You know, x could be some input, maybe the time of year, and y is the amount of rainfall in that year. Okay, and I'm just going to draw some points. Okay, all right. Okay, can you see those points well enough? It's a bit points on points, right? Okay, so let's say our job is to come up with a model to predict the rainfall based upon this data that we have. Okay? There are lots of ways we could go about this problem. All right? So one thing we talked about as an example was regression. Okay? And this problem is particularly, it's a more or less a regression problem, meaning we're trying to fit data points in a way that's meaningful. And what I mean by meaningful is we want a model that generalizes. Okay? If those data points there, maybe they are from data points we have measured, you know, we looked at the rainfall on day 1, 2, 3, 4, and 5 in Tallahassee, and it came up with this plot. Okay? We could easily write a piece of code that regurgitates this data back to us and say, hey, on day 3, this was the rainfall. But that's not very useful in the future, right? For being able to predict future rainfall. So what we want is a model that makes some kind of prediction, right? Now, using my brain, I pretty easily just drew that curve through there, right? But internally, I'm having a lot of considerations that I'm not maybe aware of when I'm drawing that line in a smart way. But we have to be extremely clear when we are coding it into an algorithm to do this, right? Because one thing we could do is we could make an algorithm that says, hey, fit all those points as best as you can. That's something we would do with our optimization algorithm. Do we recall there were four different components of using machine learning for a task? Anyone remember what those 4 were? Anyone? I hear people flipping back. Christian, I see you flipping back in your notes.
Data, model, cost function, and optimization algorithm?
Yes, yes. So the data, model, cost function, and optimization algorithm. I forgot to write it down, so I just asked you. I'm just kidding. So the cost function determines how good our algorithm is. So we could say our algorithm, thank you so much. So we're good here. All right. How are we doing on frames? Yeah, good, awesome. So our algorithm, we could say, hey, fit those points as best as possible. Okay? maybe that's a good idea, maybe that's not. I'll tell you, if we had the right kind of function we were trying to fit, instead of doing that, it might decide to do like that. That's a really good fit of all those points. It's a function, right? Is that good? Why? Why is that not good? It's an overfit. We know the term overfit. Why is it over? So it's overfitting all these points. Why is that bad? It fits really well. What do you mean overfit? What nonsense is this? Why is overfit bad? Yes?
Because using this, whatever your machine is going to try and do is going to try and meet that exact point. So
Yeah.
it'll start, like, I assume, like, oscillating between your high and your upper and higher points.
Yeah. So you're pointing that you're saying that it's going to oscillate like this, and that's not like seemingly what's actually happening in the real system, right? It's not generalizing well. Okay. So this is a great fit does not generalize well, okay? And so much about machine learning is about generalizing well. Again, if it's just about memorizing data, that's easy. We just put it in memory, say, hey, what's the data? There it is back to us. But it's about what happens in between these data points that we care about. And also, here we're assuming that each of those points is sacrosanct. It's perfect, right? In the real world, there's something called noise in our measurements, okay? You could measure on the same day the temperature and get many, many different readings. At the same instant, in the same room, you can get many different readings, okay? The sensor itself can have noise in it and how it responds, right? So you could have all kinds of data points that cannot even possibly be perfectly fit, right? This could be your data, right? Right? So we couldn't possibly go through all those points, right? So, and yet we're pretty good at saying, hey, here is our trend line. There's X, there's Y, there's our trend line. Okay, so what we're trying to do in machine learning is balance two specific things, okay? We want to fit the data well, but we don't want to overgeneralize, okay? So we want to fit the data well, and we want to be able to generalize. I apologize. So in ML, we want to fit the data well, but also generalize. Okay. All right, that's what we mean. That's what we know when we look at that. Like in our heart of hearts, we know it's bad. Okay, when it does all those data points in all those weird ways. But specifically mean it generalizes well. How could we possibly know that in a mathematical way that something is not generalizing well? Any ideas? Any ideas? Yes?
The power of the function that it's using.
The power of the function that it's using. Tell me a little bit more about that. That's interesting.
So if you have like if your highest coefficient was like to the 16th power, like you're probably overfitting.
Yeah. So you're saying if you had like a polynomial fit and you had a 16th power model, x to the 16th, it's probably overfitting. It might be, but how do you know it doesn't need a 16th power model?
Depends on like the phenomenon. You have to have some prior about the phenomenon.
Yeah. So he's talking about having some kind of prior knowledge about the phenomenon. That is helpful. Like if you know something about this data in general, then you can restrict your function to something that's realistic. Angela.
Would choosing like a fit that's statistically like significant, like comparing your data points to like the best fit line, would that be another way mathematically to like check that you have a good fit?
Sorry, could you repeat that beginning of that one more time? So yeah.
Like making sure that it's statistically like significant.
Yes. So tests for statistical significance are definitely a tool you can use. I think of those more in traditional statistics. People have heard of maybe a student t-test or maybe a p-value. Those are statistical tools, ones that are not as relevant to what we're doing here. Typically those are like binary classifiers. Like, this is in a like if you see a medical study, like we showed with statistical significance that this drug improved treatments for this, right? We'd have two populations and two people in different groups, and you'd say, is there a statistical difference between these groups? And a p-value would do that. That's good stuff. But we have another way here, okay? All right, so it goes down to this. When we made this fit, or this fit, we were making those fits based upon every data point that we had, okay? And the process of making that fit is called training. So training. Training, okay? Training is the process of finding the best model parameters that fit a training set of data. Okay? A training set. Question. Would be including outliers for this? Oh, the outlier question. Great question. So before we ever get to deciding what data set we're going to use, we have to decide what goes in the data set, right? So if you are given a pile of data from your boss and you're like, what's your name? Natalie. Like, Natalie, I need a machine learning model for this data set. And he just plops this data pile in your lap, okay? People who are pros in machine learning know not to just take in that data, run it through their algorithm, and go. They take a look at the data and is like, is this data any good? Is this data representative of what I need? These are other topics we'll talk about. And it's up to you whether or not you want to include an outlier. Is predicting those outliers part of what you want to predict? So that is up to you. For now, we are just throwing data in, say, this is what I want to fit, and we'll see what happens, Natalie. Okay, good question. So just as a little aside, so thinking about what data goes into training your model is a big deal, and we'll talk about that in a second, not only for what we call the training set versus a test set, which is the rub here. I'm trying to remember the exact details. There was a study where scientists were trying to use machine learning to detect childhood cancer from brain scans. And they came up with these statistically good results that they had a good way of predicting this one has cancer, this one doesn't. But it turns out it wasn't detecting cancer, it was detecting children. Okay, so you need to make sure that the sample of data that you're bringing to the table is relevant to what you actually want to solve. Okay, and we'll get that in just a second here. Kind of jumped ahead, but if you have all of this data, Natalie's been given this pile of data. She's come up with a model. Okay, there's no reason she has to use every single data point for training, right? She could look at this data right here and say, you know what, I'm going to randomly withhold some of these data points. This one, and you can select it randomly, okay? Right? In fact, you should select it randomly, right? So you can withhold data from training. Okay. Why might that be useful? Well, sure, you can train on all of this other data that's around there, okay? But then, once you have trained your model, you then test your model against the data you didn't train it on. right? So you can divide your data set that you are given, that Natalie's been given. I'm making a lot of assumptions about your data set, Natalie. Hope that's okay. All right. And withhold a set that's a test set. Okay? So good practice is you can test generalization by withholding data from the training set and use it later for testing or a test set. Right? Because theoretically, how good your fit is for your training set, that's important. But you can also test it on the test set. How good does it fit that test set? And if it fits the test set well, it wasn't part of the training, that means it's probably generalizing better, right? So there's this kind of famous looking plot here. Okay? Where you have, on this axis you have error. Okay? And on the horizontal axis, we have how complex your model is, okay? Jack was saying it could be like the order of your polynomial fit, right? There's a word for that. It's called capacity. Capacity. You know, a linear fit is very simple and has very low capacity. You can only fit lines, right? So if your true model is something curvy, it ain't going to fit it. It doesn't have the capacity for it. But I'll tell you, there are lots of great times you want to use linear fits. They're still phenomenal, okay? But where would that be on this spectrum? The low capacity, right? Okay? And up in the high capacity, you could have higher order polynomials. You could start to have neural networks, okay? Which have a lot more, and the idea is that these things tend to have a lot more parameters, okay? So they tend to have higher parameters, to have more parameters, sorry. Okay? So here in general, so you have your error, okay? And here is as your capacity increases, your training error will decrease. This is your training error. The data set you are training on. Okay? That's supposed to be smooth. Let me do better than that. Like asymptotically approaches 0, which makes sense, right? If I had a giant high-capacity model and 10 data points, it better be able to fit those exactly. But what's the problem, right? What might it not do well? Generalize. Generalize, yes. Whoever said that, right? So how do we can compare it then to the test error, which will look pretty similar until it starts to get worse. Yes?
Are there units for capacity?
There's something called the VC dimension. Okay, I wasn't planning to get too much into that today. They talk about it in Chapter 5 of the Goodfellow text. Going to try to pronounce the name. I'm not going to try to pronounce the names for what VC stands for off the top of my head. That's going to offend V and C. But it's not really. I don't know if it's meaningful to talk about it in terms of units, like physical units of measure. That's a good question, though. That's a good question. Really, you can think about it in terms of a relative thing, like maybe a number of parameters. If we're talking about you're my go-to guy for polynomial fits, Jack. Okay. Okay. Yeah. Yeah. Thank you. Thank you. So it could be just number of parameters in a polynomial fit: linear, quadratic, cubic, quartic, quintic, etc. Right? For a neural network, again, we haven't really talked too much about neural networks. Just showed just a little bit. They all have these little weighting factors, their parameters, these W's, and So it could just be the number of those parameters. But even that is imperfect because the structure of a neural network can matter too. So how do you measure that? Good question. But I think relatively speaking, you can view it in sort of a continuum. Okay. What's your name? Connor. Thanks, Connor. That kind of answer your question? Yeah. Kind of. Good. All right. So what we have here, right at the bottom, excuse me, I want a color. Right at the bottom here, right at the bottom of this curve, okay? That's a good model, okay? So it's neither, here we have, on this side we have an underfit. And here on this side we have an overfit, okay? This is the sweet spot. This is what we are shooting for, the best generalization we can, okay? So we could actually test this in sorts using, again, this super sophisticated, okay. All right, got a Survivor fan in the chat. That's great. Good to have you, okay. All right, so let's see if I can get this going, change this over. So I'm going to see if I can get this to work here. Hopefully people can see it in just a moment. This very sophisticated software, Microsoft Excel. Okay, oh yes, yes. Just do a little bit of examples of machine learning here, okay? All right, again, so the goal here is to explore the process of fitting data. And yes, we'll be doing this in a simple example with these relatively simple models, but these concepts extend to extraordinarily complicated models as we get deeper into the process, okay? So what we're gonna do is we're gonna make some data, okay? We're just we're gonna synthetically make this data, and I'm gonna make it for some phenomenon I know is quadratic, okay? So hopefully people can see so I'm gonna have a quadratic model. And a quadratic model is going to have three parameters, the x to the second, x to the first, x to the 0 parameters. Okay? It's probably, I'm going to see if I can zoom in here, folks. You can probably hardly see that on the recording. Zoom. Let's go 200. Go crazy. There we go. Now we're talking. All right. Hopefully we can see that a little better, Nick. How are we looking? Okay. Good. So quadratic model, we're going to have let's go back and forth to the screen here. Quadratic model. Boom. So we're going to have a quadratic model where y is going to be equal to a2x squared plus a1x plus a0. Okay, where x is our input, y is our output, right? That's going to be our true model. But we're going to get a few data that's sampled from that model. Okay. So we're going to have a2, a1, a0. I'm just going to define this model as 1, 0, 2, 3. So therefore, if I have some input x, some data, okay, and I want my y value that I'm going to draw from that is going to be equal to x. So it's going to be, a2 times x squared. I'm going to make this a absolute reference. Does people still use Excel, right? Yeah. Okay, making sure. I don't know how much people have moved on from this technology. It's wonderful. Plus a1 absolute reference times x squared plus there. So if x is 0, that's 3. And that's great. So now let's randomly grab data points between x equals 0 and x equals 1 using the rand command. Rand. Boop, 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 boom. Great. And we'll grab ourselves 5 or 6 data points here. All right, there's our data. Okay? So it keeps randomly redrawing the distribution every time I refresh the page. So we'll just deal with that. And now we're going to insert a scatter plot. There we go. There is our data. Okay, my friends, I don't like the values I chose. I'm going to choose different values. Let's see, -2. I like that much better. And I like this much better. Okay, now we're talking. All right, and I'm going to do -4, -3. I'm just doing some magic right now, okay? All right, now I'm going to make the axes, I'm just going to make them not move around. I'm going to go from 0 to 5. All right, yeah, 0 to, let's go from 2 to 5, 2 to 4. Sorry, I know it's the most exciting part of the lecture here. So we have this data here, and I'm going to make sure that this stays here. Format axis. When I mean doing things from scratch, I mean from scratch. Okay, 0, 1. Cool. All right. This is our parabolic data. Okay. All right. There's our data. Cool. So, question is, how do we fit this data? Now, we know it's parabolic because we made the data, but maybe this data comes from actual measurements. So, what we will do is we will we'll start with the simplest of models, a linear regression. So let's add a trend line here. There we go. It's a nice linear trend line. There we go. Maybe it's a good fit, maybe that's a bad fit. We'll see. Let's go and add to our trend line. Let's go to a polynomial trend line. Parabolic. Oh, it's perfect, unsurprisingly, right? That generalization is pretty darn good, but we don't know that yet, okay? But like Jack was talking about, you could go up to like a 6th or 16th order. Let's do that. Excuse me. 16th order. Okay. For my trend line. Okay. And you can tell it's still doing really well, but we don't have any noise in here. That's the issue. Here. Let's add a little bit of noise. Plus rand times 0.01. Okay. There we go. Okay. Plus 0.1. Here we go. Now we're talking here. So we've added a little bit of noise. Basically add a little bit of a random noise to it. Let me see if I can get this working here. Yeah, this is on purpose, I swear. Okay. All right. So let's go back to our trend line fit. Here we got noise. We did it from scratch. Thank you for dealing with your patience with me. Okay. So let's go to an order 1, order 2 fit. Pretty dang good, right? Pretty dang good. Order 3, doing okay. Order 4 gets a little weird. Order 5 gets a little strange. Order 6, a little strange again. Let's refresh everything. Okay, here we go. This is what happens when you have higher order fits. You can literally see how bad the fits can get. And he has no idea that it generalizes poorly, because why would it? It's only trained on the training data. But the good news is that all this stuff is the training data. What we can then do is take this and add to it some test data and plot that and add that to the series. So let's go select data. Let's add a series. The x values are that. The y values are that. Okay? There we go. And you can see how terrible it is on the test set. All right? So typically, when it comes to modern machine learning methods, at least when I learned machine learning, is that if you have a big data set that you're trying to train and test things on, about 90% is the training set. And the last 10% thereabout is the test set. Okay? That's what I typically, yes?
Oh, no, the way I was learned in some other classes
Yeah.
was 70-30 or 80-20.
Yeah, look, I think the standard might have changed over time, but we'll get to that point. But I was giving you all, it's not like 99-1. It's not half and half. Okay? But yeah. Sorry, we got a ringer in here from another class. Anyway, it's good. So anyway, so we'll get to that more, but that's the idea of how you can measure generalization. Does that make sense? Okay, great, awesome. So now the question is, how do you select a training set versus a test set? So you want to make sure that you are selecting a good training and test set. So to select a training, thank you very much. Oh my goodness, what am I doing? Okay. and test set, you want to select a representative sample. Okay, and so the typical assumptions you want to make for all the theory that goes into learning theory is that the data points that you're getting are independent. Okay, they're not dependent on each other. Okay, and they're identically distributed. Okay, so we would typically call this, we want them independent and identically distributed, or IID. Okay? So the phrase IID means that, and it applies more than just training and test sets or any kind of data set. If you take any of Dr. Oates' classes in probability, it's a big assumption of a lot of the methods that you use. That means that one data point is not dependent on the other data point. That by grabbing this data point, you didn't affect that other data point. You make that assumption. Okay? And also they are from the same distribution. Okay? And that's something we want to, and when I'm talking about distribution, I'm talking about probability distribution. Okay? People here have heard of the concept of a probability distribution, I would assume. Okay? If you need a little bit of an update, I believe one of the early chapters of Goodfellow, the Goodfellow text, has a nice, somewhat, I think reasonably thorough reintroduction to probability theory. Okay? But typically, we think of a distribution, probability distribution, as you had some independent variable x, and then some probability that you've selected that independent variable x. Looks like maybe a bell curve. Okay? That's a normal distribution. Normal distribution. You could also have, over a certain interval, flat and down. That's a uniform distribution. Okay? Okay. So what it means is that if you are trying to select a test set or a training set, and let's just say that your training set has some kind of probability distribution, okay? You want to select from it something that might look like that. You're selecting fewer of them, but the same general shape, okay? You wouldn't want in a test set to test only stuff over here. That would be a poor test of the generalization. So the distribution is identical, meaning that the shape where the data comes from is identical. Okay? All right. So now this idea of a distribution is a really powerful and general one. I'm only going to talk about it in generalities today. Okay? But when it comes to machine learning, it's very important to kind of understand the concept of a distribution, because it drives a lot of your choices about machine learning. Okay? What kind of machine learning methods you're going to use, what kind of models you're going to use, and also some important concepts like, is your model going to be a good model? Some might ask you, hey, what's the best model? Is there a neural net? It depends. It always depends. In fact, there is a theorem that says it depends. Okay? And it's called the no free lunch theorem. Okay? There's no easy answer. There's no always best answer. Okay? Concept of there's no such thing as a free lunch is that, I guess, even if someone buys you a free lunch, there's a cost at some point down the line. I don't know. But so there's no such thing as a free lunch. And what this means is that there is no machine learning model that generalizes better than every other machine learning model. Okay? That no matter how good you think your machine learning model is, like, oh, I created this beautiful polynomial. Well, for some other task, this type of polynomial is going to be worse than some other type of polynomial at some other task. Okay? It will generalize more poorly. Okay? So no model outperforms every other in terms of generalizing performance. So it means that even in this world of machine learning, which is so much more sophisticated and advanced, you still have to be thoughtful about what model you choose. Okay? This happens all the time when people get whiff of that I know something about machine learning. Debatable, but people come up to me and say, hey, what should I use? Should I use a large language model for this data? And I was like, whoa, 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 whoa. How much data do you have? Is this a good thing that you want to use? There's probably some other model that might work better. There are certainly things large language models are great for, but not everything, right? So there are some models where sometimes you're like, linear regression is absolutely the way to go, okay? But it's called the no free lunch theorem, okay? So other concepts. So now, when it comes to training, okay, so training fits model parameters. Okay? And in that case, an example is our quadratic fit. So, for instance, so if y is equal to a2 x2 squared plus a1 x1 plus a0, where our parameters, our decision variables, the three decisions that were made in the optimization are a0, a1, and a2. That is our decision vector. And these are chosen via optimization that minimize cost. Okay? Those are the decisions in the decision vector. Those are the parameters. But they are not the only decisions that you have made. We made the decision to make it quadratic, right? That's a higher level decision that we made, the number of parameters, the Wernickean parameters, okay? There is a name for this higher level parameters. They call them hyperparameters, okay? In this case, the hyperparameter was 2. We want, or 3. We want three model parameters, okay? So higher level decisions about models and training are called hyperparameters. Okay? They are not typically optimized by the optimization algorithm. Why? Because to know if they worked or not, you have to run an optimization algorithm. So you have to run an optimization algorithm inside of an optimization algorithm. Can it be done? Yes. Is it practical to do? Not often. I mean, there are things you can do. You can say, I have this one hyperparameter I think is very important. It's the number of polynomial terms. OK, I'll try a whole bunch of them, see which one generalizes best. That's reasonable. But as these models become more complicated, there are a lot more hyperparameters. And it's just not practical to try a whole bunch of them or optimize them. Okay? At least it's less common to do. All right? So they're called hyperparameters. All right? So, any questions about this so far? Give me the basics here. So, sounds like you're you're familiar with the concept of overfitting. You don't want to overfit. Why? Because it doesn't generalize well. What defines whether it's going to generalize well? Well, your choice of hyperparameters. Okay? Your decisions about their model. Okay? So we want to be very conscious of this when we are choosing our models. So let's get to once we've chosen our models. So Gesundheit. Training models. This is where our optimization comes into play. Optimization. Okay. And our cost function. We talked a bit about our cost function last lecture in our introductory lecture. How are we doing, Nick? Yeah, no drop flames. Good, good, cool. All right. So when it comes to training our models, we talked a little bit about last time how we might have some set of decision variables, some decision, W, and we'll have some cost function. Now, in the textbook, they call the cost function J of W. Okay, that's your cost function. So J of W. Now, in reality, we don't necessarily know what this looks like. We know from trying different decisions and see how well they work. We try the decision, it worked this well. We try the decision, it worked this well. But on some space, someone theoretically, it's possible theoretically to know that it looks like this, or like it has some shape to it, okay? That clearly, some decision has the best cost, okay, right? That is the best decision, lowest cost. Okay. And in order to do that, we use an optimization, which basically tries to find a W that minimizes the cost. Now, how do we know if we've minimized the cost? Question. Natalie. Oh, who gets to decide the cost function? You do. Okay? And the cost function that's very typical, okay, for fitting data. So here's an example. Look at me, freewheel in the lecture. Give me a question, give you notes. Okay. So typical cost might be fitting the data by minimizing the difference between your predicted data, your prediction of the data, and the data itself. Okay? I talked about a least squared error. A more typical way of talking about it is something called a mean squared error, or MSE. This is great for a number of reasons. The idea is that your MSE, put this in the corner as an example, that if you have some number of data points, m, so it's 1 over m times the sum across all your data points of your prediction of what that data point is minus your actual data point for all your data points, and you square it. That way, when you're close, that error is 0. You sum up all across all the data points, boom, mean squared error. This is the number of data points, of training points. Okay, little continuation of last lecture. Very common, okay, for a number of reasons. Also, it's so mathematically simple. For linear for models that are for certain types of models, you don't need your training algorithm is super easy. It's not even iterative, okay? But what we talked about was the idea of so how would we find the minimum cost? Assuming we did not know, we did not have this plot showing us what it is, okay? Well, you could try every set of W's. Try them all. Within some gridded resolution, you could try, I'll try this. Try them all, okay? And see which one is the best. There's a problem with that. What if you have more than one decision to make? Okay, let's say instead of one decision, you have 2 decisions. That means that you would have decision 1, decision 2, and then some cost, which is based upon both of those decisions in the decision vector, right? And so this thing is a surface. Now you want to do what we call a gridded search, the thing we were talking about. We want to check this. Okay, I'll stop. Okay? It's going to take longer, right? What if you had 3 decisions? Now the number of decisions you have to make, let's say there were n points on that line right there. Here we had n squared. For the linear one, we had n. For one decision, we had n. Now we have n cubed. Some of these neural networks have 1 billion parameters. We don't optimize that way for a reason. These gridded searches don't work well. They don't scale well for this for large numbers of decisions. Okay. However, it's the best way to know if you've got the best one. Because how do you know? So anyway, that's one thing. But let's assume that this cost function is smooth. How will we know that we're at a best decision? Take the derivative. See if it's 0. And then see if it's concave up. Or typically just assume it's concave up at the end of the day. But anyway, it's at this point, the derivative of j with respect to w is 0. No slope. Slope is 0, right? There, the partial derivative of j of w with respect to w is equal to 0. Okay? There's a name for that. So that in order to know if you're potentially at a minimum, it means you must have that derivative equal to 0, or very, very close if you're doing this numerically. Okay? So we call this the first order necessary conditions, or the FONC for optimality. Okay? Meaning that you could say the partial derivative of j of w with respect to w, all your decisions, is 0. Now, you've all taken calculus. You know, technically speaking, it could be at a maximum or at a critical point. So how do you determine if you're at a minimum as opposed to a critical point or a maximum? Was that? Second derivative. The second derivative will tell you if it's concave up, therefore the bottom, versus top. Okay? Now, in practice, because the way that we try to find this condition, you're descending down the cost function. We often, Nick, do you ever check if it's concave up in any of your models? You never have to, right? Right. In practice, in machine learning, we tend to assume we're at a minimum. But if you need to, you can do a second derivative, and that's called the second order sufficiency condition. Okay? This is called the first order necessary condition. Why? That's a first order derivative. That's the first derivative. Okay? So that must be true. Like, in order to have a chance, that necessarily must be true to be a minimum. But to know if it's sufficient, you also have to check if it's positive. So we call that the second order sufficiency condition. I'll put it off to the side. The second order sufficiency condition, or SOSC, which means that the second derivative of j of w with respect to w is greater than 0. Question?
For the purpose of this class, can we just always assume it's going to be concave up?
Sure.
Okay.
Sure. I would love a machine learning person to tell me, like, oh my goodness, Christian, you have no idea how much we have to check the second order sufficiency condition. I would love someone to tell me, but that's just not something I've encountered. So now, if you're doing theoretical optimizations, you technically want to check, but if you're trying to say, oh, this proof says that I'm going to have this condition, but so how are we doing on time here? Ooh, okay, good. So the first order necessary conditions. So that tells us if we're at a minimum. Does it tell us if that we're at the best anywhere in the entire function? It doesn't. You're shaking your head. Why?
Because there could be false, like, pitfalls.
There could be false pitfalls, okay? Yeah, you're absolutely right. Here's an example. Let's say this is our cost function. J of W. Whoa! Our derivative is 0 here and here. One of those is better than the other. Right? You call this is the local minima. This is the global minima. Okay? So both of those will satisfy the first order necessary conditions and the second order sufficiency conditions, right? And that's important to be aware of, because a lot of the methods that we work with in machine learning, a lot of them can't guarantee that you're not right there. It's very hard to prove that you're not there, that you're there. Okay? It's very hard to do. Okay? We talked a little bit. Does anyone remember what we talked about gradient descent last time? Yeah? What did the gradient descent do, other than, I guess it descends the gradient? I answered my own question. Okay? So descend the gradient, right? So what you do is you start with an initial guess, and you say, oh, I'm starting there. The slope is down that way. We want to try again. Therefore, let's move to the right. The slope is still pointing down to the right, so let's move to the right again. And as the slope gets shallower, you take smaller and smaller steps until you get there, right? So if this was your initial guess, whoop, it takes you there. Who gets to choose the initial guess? We do, right? But if you chose initial guess over here, whoop. So what's something you can try to do to try to come up with a better minima? Any guesses? Any guesses? Well, literally, yes. Take multiple guesses at the start. Rerun it with a different guess. See if you get a better answer. Okay? So some problems, for some machine learning problems, local minima, not a huge deal. For some of it, it's a huge deal. Yes, Angela?
Is there not a way to like manipulate the like gradient descent like algorithm to continuously check like maybe from like a whole region, like if you have like from 0 to your like greatest, I guess W would be your like decision vector.
Yeah.
Could you have it choose like or check that entire thing to find
You
the
could-
global minimum?
You could do all kinds of crazy things. You could be creative. So the question is, are there fancy things that you can do to try to not get stuck in a bad local minima, right? Absolutely. You could randomly like restart the algorithm. Like, I expect something better. Choose another guess and start again, right? You could mess with the step size. So how far you step with each guess, so it might skip over these little bad regions that we don't want. But then later, move down the step size so it's smaller, so it'll sort of figure it out. So I think there are momentum-based methods that say, hey, when you're taking larger steps, keep taking larger steps, and then change your step size so it's smaller later on, as a way to sort of manipulate our way out of finding those local minima. But that's something you got to be aware of. Did that answer your question?
Yeah.
Yeah. Question?
So for the local, because you have a local maximum that's between the two minima.
Yeah.
So like if you did the first derivative, obviously it would look exactly the same.
Correct.
So because you say that the second derivative is not like required, so how do you avoid that without like testing the second one if you just don't think it's necessary?
I love this question. The question is, there's a local maximum in there, and I've just been poo-pooing and taking a dump all over the second derivative, you know. But look, if this would pass if we don't check it, how do we end up? We know we're not end up at a maximum. Well, here's the thing: with a gradient descent algorithm, unless your guess happened to land at the very tippy top of that at minimum, it'll see, oh no, there's a gradient there. I'll start going over, then it'll slide down, right? So I can't remember a time where I accidentally ended up at a maxima in any practical problem, but point taken. Okay? And certainly you can use second derivative information, by the way, to help you determine your step size if you really wanted to. Like if you're like, actually it's not very, very curvy, you know, maybe I want to change my step size to be larger or smaller. You could use that, but you don't have to, but we often don't check to see if the sufficiency condition. Okay. Okay. Good. That's your question? Thank you. All right. Okay. So the way that we typically go about finding the minimum is via gradient descent. So finding the minima using gradient descent. Okay? So one thing we do want to cover is a little bit of basics of calculus when there are vectors involved. Okay? So we all know that if you have a function, let's say some function, we'll call it j of w, okay? And we take the derivative of j with respect to w, and j is scalar valued, which we've said our cost function is. It returns a single number, a scalar. And w, let's just say in this case, is a scalar and not yet a vector. Okay? The result of that is a scalar. Okay? If you take the derivative of a scalar valued function, valued with respect to a vector, and I'll just indicate it's a vector this time with a little bar on top. Okay, that's going to give you a vector, specifically a row vector. Okay. Sorry, not a scalar. That should say vector. I'm so sorry. I probably confused everyone. That's just a vector. You take the derivative of a scalar with respect to a vector, you get a vector. Okay? Particularly a row vector. So what that looks like, and this is also called the gradient. All right? We're talking about gradient all the time. That's what a gradient is. So if w is a vector with w1, w2 up through wn, okay? Then the gradient, sometimes drawn with the capital the upside down triangle, the gradient of j of w, and this will be a w here with a bar, okay, is equal to a row vector with partial j, partial w1, then partial j, partial w2, partial j, partial wn. This is like a little dot, dot, dot. This is an ellipsis. That's what that is. That's in wn, not a w2, wn. Okay? Yes?
Those are multiplied, added?
Those are spaced apart in a vector. So we've all taken Calc 3. We've seen vectors. Okay? Did you take Calc 3? Not yet. You're fine. You'll be fine. We have a, yeah. So they are not multiplied. Those are like, again, like you're using MATLAB vectors. You're doing comma, space, comma, space, comma, space inside of brackets. It's a mathematical vector, okay? All right, it's called the gradient. The second derivative of a function, j of w, with respect to w, where it's a vector, gives you a matrix. Okay? Okay. This is the linear algebra part of like how this mixes with calculus, okay? So this would be the partial of j with respect to second derivative of j with respect to w1 twice. That's the second derivative of j with respect to w1 partial w2. This one is partial j partial w2 partial w1. This is partial j2 partial w2 squared. You'll notice along the diagonal, along the diagonal, you have all of your w1 squared, w2 squared for your second derivative. And then this is going to be partial j, partial w1, partial wn. This would be partial J, partial W2, partial Wn. Then down into the last row, you're going to have partial J, partial Wn. That should be a N. I apologize for my handwriting today. That's an N. This is partial W1, partial J, partial Wn, partial W2, all the way to partial J, partial Wn squared. That is your matrix. The key thing to note is that along the diagonal are your second derivatives with respect to the same variable. You'll notice that along this row, all the W1s are the same, all the W2s are the same, all Wn's are the same on this row, and the columns are the second number. Okay? We won't compute a lot of these in this class, but I just want to tell you that this is what the second derivative looks like. Okay? And has a name. The second derivative of a scalar with respect to a vector is called the Hessian. Okay? And we talked about how it has to be positive for it to be a local minimum, for it to be a minimum as opposed to a maximum. How can a matrix be positive versus not positive? Anyone who took linear algebra know the answer to this? I mean, it's a whole bunch of numbers, not just one number. You? Yes, yes, yes. So the term is what's called positive definite. If you take a linear algebra course, we won't talk too much about this here, but the idea is that if this matrix is positive definite, it's a property of the matrix, then the whole thing is positive. And therefore, I don't care how multidimensional this space is. If it's positive definite, it's a bowl in that area. It's concave up as opposed to concave down. And what that means is all eigenvalues have positive real parts. That's as linear algebra-like as we're getting today. That's just so you know about it. Okay? I won't expect you to compute an eigenvalue by hand or anything. Okay? That's a concept from eigenvalues. That's a concept from linear algebra. Okay, we are closing in on the end of time. But the thing I want you to know is that when you take your derivative of your cost function with respect to your vector, you get a vector out. Okay? So when you're doing gradient descent, you're going to be computing this gradient. Let me just give you an example, just in case you haven't done it in a while. Here's a gradient example. Let's just say that our cost function j of w, it would never actually be this, but this is a simplified one that we can write out, is 3w1 squared plus w1 w2 plus w2 squared. Question is, what is the gradient of j of w? Well, it's going to be the partial derivative of j of w with respect to w1, and then the partial derivative of j of w with respect to w2. And these are just partial derivatives. If you haven't taken a partial derivative in a hot minute, it's the easy derivative. Okay? It's where you only look at this variable, and everything else is treated as a constant. Hallelujah. My favorite kind of derivative. My least favorite kind of differential equation, though. Partial differential equations are nasty. So partial j of w with respect to w1, here on this term here, w1 is there. It's a squared, so it's going to be 6w1 plus this term here. W1 is multiplied by W2, which we treat as a tax form constant. So it should just be the constant W2, and plus that's a constant. with respect to W1. So 0. Okay. Sorry, you're all getting your calculus refresher for no reason. Then partial W2. This is all a constant. This constant is going to be W1, and this is going to be 2 times W2. So 2 W2 plus W1. So your gradient of J of W is going to be 6W1 plus W2, space in a vector, 2W2 plus W1. There you go. So if you wanted to know where the minimum of this function is, you would need to find where this term is equal to 0 and this term is equal to 0. Okay? We could solve it right now. This is 2 equations, 2 unknowns. We could find it. We're not gonna. Not that hard, obviously. Okay? But we will solve that optimization problem super easy, knowing the minimum of that function, right? But on Thursday, we will, in Python, use code up gradient descent to do it for us. All right? Hope to see folks on Wednesday at 9 p.m. Optional. See you remote. I will send out Zoom links to all of these courses. Thank you so much.
Do you know roughly how long Wednesday night is going to be?
12 hours?
Okay.
No, I'll try to shoot for an hour-ish. Okay. Okay. So you know, great question. Hey, come on. Second here.